So hello students, so let us continue. So let us start with the solubility of ionic compounds. Solubility of ionic compounds. So let us discuss the solubility of ionic compounds. We know what is an ionic compound is all about. In an ionic compound, there will be cation will be there and anion will be there. And cation and anion are strongly attracted each other by electrostatic force of attraction. So that's the way you can see in an ionic compound. Now let us think how the solubility, how ionic compound going to dissolve in a solvent. So let us think two cases. In ionic compound, an ionic compound like sodium chloride, ionic compound like sodium chloride, when it dissolves in water, it dissolves, it easily dissolves in water, right? But now you talk about NaCl in benzene, it do not dissolves, it do not dissolves. So from here you can think an ionic compound like sodium chloride dissolves in water, but now there is sodium chloride which do not dissolves in benzene. So why it's so? That's the way a student can think. So here now sodium chloride, which is now definitely consists of existing as cation and anion. So they are now charge separation is there. One is now positively charged ion and other one is a negatively charged ion. In the case of water, we know water is a polar compound. It's a universal polar solvent. Where oxygen is more electronegative, so there will be a partial negative charge on oxygen, and hydrogen is partial positive because of it is less electronegative. So there will be always an interaction between the cations and the negative polar center of water and anion and positive polar center of water. So there is always a solute. Let us discuss now. Sodium, consider sodium chloride as a solute. So there will be always a solute solvent interaction will be there when you are trying to dissolve a sodium chloride in water. That way it dissolves. Okay, that why there is a no so an ionic compound like sodium chloride dissolves in water. I will discuss what the important thermodynamic parameter involves in the dissolution. Let us understand this point. If you want to dissolve a polar solute in a polar solvent, no, in any solvent, it has to be, if a polar solute needed a interaction with the solvent. A solute has to interact with the solvent. If it is a polar, then it requires a polar solvent to dissolve in it. That why a polar solute do not dissolve in a non-polar solvent like benzene. Okay, so that's a case where there is a polar solute, polar ion polar interaction is there because ion sodium chloride existing as ions. So ion and the negative center of the polar. So ion polar interaction existing there. That why no sodium chloride dissolves in water. Now, why benzene it not dissolves in benzene? Because we know the structure of benzene. Benzene is actually C6H6. Now it's a cyclic structure, highly stable structure. But now what's the problem? Here now you can see two types of bond: carbon-carbon and carbon-hydrogen. Two bonds you will see. Both are non-polar in nature. Remember, carbon and hydrogen have similar electronegativity. So which means carbon-carbon bond and carbon-hydrogen bond are non-polar in nature. So definitely a polar solute like sodium chloride do not going to dissolve in benzene because there is no solute solvent interaction. Now let us come back to the thermodynamic point. What is the important factor which influence the dissolution of an ionic compound in water? So when you talk about dissolution, remember different ionic compounds have different solubility. It doesn't mean that all ionic compounds, there are plenty of ionic compounds are there. All ionic compounds have same solubility in a solvent like water. No, it has different solubility. Some of the salt are easily dissolving in water. Some of the ionic compound moderately dissolving. Some of the ionic salts are sparingly soluble, which means very less soluble. So different solubilities exhibited by this ionic compound. Why it's so? Let us think. Two thermodynamic factors which influence the dissolution of an ionic compound in a solvent like water. What are they? So let us check. Let us represent that as a delta X solution. We can say solution enthalpy or no The change in enthalpy associated with the dissolution of one mole of an ionic compound in a suitable solvent like water. So two factors will come into play. One is delta H lattice, that we will call lattice enthalpy, and another factor we generally represent that U0 as well. That's let me represent in terms of thermodynamic term. This delta H always we use. That means change in enthalpy. Change in enthalpy associated related to the lattice enthalpy. So here delta H 0 plus another factor is delta H. You think about the solvent is water. So let me represent hydration enthalpy, or otherwise you can say a solvent, delta H solvent. That solvation enthalpy for it. So these are the two factors which influence the dissolution of an ionic compound in water, or generally you can say in a solvent. One is lattice enthalpy, other one is hydration enthalpy. Now let us think how it influences. Lattice enthalpy means the two things you can see when you talk about dissolution of ionic compound in water. One, this cations and anions has to be separated from each other. We know they are strongly attracted each other. So ions has to be separated so that they can have a chemical bond with the water. So this is nothing but ion polar chemical bond interaction. So if they want to generate a chemical bond like this, the ions has to be separated. The amount of energy that required to separate an ionic compound into isolated gaseous ions, that what we will call lattice enthalpy. So lattice enthalpy is going to be one of the important parameter. Sometimes lattice enthalpy may be generally high, but still that can be compensated by hydration enthalpy, because once ions are separated, the ions forming a bond with the water. That means a chemical bond is formed between the cations with the polar center of the water, also anion with the polar center of the water. So there is a ion polar interaction develops in a solvent. So we know when a chemical bond is forming, thermodynamically energy will be released. So hydration enthalpy are generally negative in nature. So you always get a negative value according to thermodynamics when energy is released. Delta H, hydration enthalpy. This stands for standard condition. So delta H hydration enthalpy will be negative, and lattice enthalpy will be positive or negative depending on what we are talking about. Here we talking about ions has to be separated from each other. So that suggests it is the amount of energy that is that's required to separate an ionic compound into its isolated gaseous ions. So delta H lattice enthalpy will be positive here, because you have to provide energy to separate into gaseous ions from an ionic compound. So that the summation of these two will influence the enthalpy of solution. If an ionic compound want to dissolve in water, the next delta H value, you sum these two, delta H lattice enthalpy plus delta H hydration enthalpy, the sum should be negative. Delta H negative value for solution enthalpy, or the enthalpy of solution. If that is negative, this value is negative, means that favors the dissolution of an ionic compound in water. If these two values are almost comparable, still you can dissolve it. Sometimes a small heat will give that energy that required to dissolve. So these two factors definitely playing important role. Let us now think about lattice enthalpy. If lattice enthalpy is higher, if delta H lattice is higher, if it is higher, means a student has to think so much of energy need to supply to separate into ions, which means higher the lattice enthalpy, lower will be the dissolution, of an ionic compound in water, in generally a solvent. Next, hydration enthalpy. Sometimes you think lattice enthalpy is such high, but hydration enthalpy we know it's negative. So net effect if hydration enthalpy increases, that always gives a negative value here. So higher the hydration enthalpy, that favors the Dissolution of an ionic compound in water. Dissolution of ionic compound in water. So now you can think what are the favorable factors. We require lower lattice enthalpy. If the lattice enthalpy is less, lower means that's favorable. That will be more soluble. That tend to be more soluble in the solvent like water. Then hydration enthalpy. If hydration enthalpy large negative, if more amount of energy is released during a bond formation between the ion and the water, we will say that's favorable. Higher hydration enthalpy, that also a favorable factor. So if these two factors, net delta H is negative, means definitely the ionic compound is soluble. Now you think why some of the salts are sparingly soluble? It may be due to the higher lattice enthalpy, because lattice enthalpy is too high that it's difficult to separate the ionic compound into gaseous ions. It will be difficult to separate. Other factor may be hydration enthalpy. Hydration enthalpy will be less, because we want more energy to be released, so that net delta is negative. That's we want. So these are the two important factors which are going to dissolve the which going to influence the dissolution of an ionic compound in solvent. Got it? So now let us we discussed about lattice enthalpy in the previous class. Now let us discuss what are the factors which influence the hydration enthalpies. Generally, you can say solvation enthalpy, delta H, a solvent. So let me represent the equation for solvation enthalpy. Solvation enthalpy will be, you have an equation to compare. Remember, solvation enthalpy is generally negative. That why negative sign put is here. Don't confuse now with that negative value. So set square divided by 2r into 1 minus 1 by d. This is the equation for determining the solvation enthalpy, or if in the case of water we can say hydration enthalpy. So look at what are the factor which is contributing to the solvation enthalpy, or you can easily think hydration enthalpy. So hydration enthalpy always, if Z is larger then delta H solvation enthalpy or hydration enthalpy will be high. So we want higher charged ion. For example, monoatomic cation, diatomic cation, and triatomic cation. So think about the charge of ion. If that is higher, that always favor the solvation enthalpy. That's one of the factor. Higher the charge of ion. Z is nothing but it's a charge of ion. Charge of ion. If charge of ion is higher, solvation enthalpy will be higher. Then R. What is R? R is a radius of ion. R is a radius of ion. If smaller ionic radius means higher the solvation enthalpy. That always good. We want smaller radius of ion. You think about a cation having smaller size. They have higher hydration enthalpy. So smaller size of ion, smaller size of ion, higher the hydration enthalpy or solvation enthalpy. So that's another factor. Then dy, what is d? D is the dielectric constant. Dielectric constant. Higher the dielectric constant, higher the solvation enthalpy. Remember, water is one of the solvent which have high dielectric constant. Higher the dielectric constant always relates in chemistry where it helps to separate the ions. Where we want to separate the ions, right? So we want a solvent which is having higher dielectric constant, so that ions are easily get separated. So these are the three factors which influence the hydration enthalpy or solvation enthalpy. What are they? Z, R and D. Higher the charge of the ion, higher the hydration enthalpy or solvation enthalpy. Smaller the size of the ion, greater the solvation enthalpy. Higher the dielectric constant, higher the solvation enthalpy. So these are the three factors which are going to influence the hydration enthalpy or a solvation enthalpy. So that's all about dissolution of an ionic compound in a solvents. Remember what is one of the universal solvents. So always you can relate no, with respect to water because no, it's such a good solvent. So let us discuss the next part, Born-Haber cycle and its application in determining lattice enthalpy. Born Born-Haber Born-Haber cycle. Born-Haber cycle. So let us discuss what is Born-Haber cycle. Born-Haber cycle knows something generally used to determine the lattice enthalpy of an ionic compound. That's the first point you can remember. Because no, it's not easy to determine a lattice enthalpy. We already saw Born-Land equation is one of the way, but still no, it's using Born-Haber cycle. Initially, it was really a valuable contribution to understand the lattice enthalpy of an ionic compound. So not only that, if you have lattice enthalpy, you can use it to determine other lattice parameter like ionization enthalpy, electron gain enthalpy, enthalpy of formation of a compound. Such parameter also we can determine. So it definitely Born-Haber cycle have a very good application in thermodynamics, especially related to the formation of an ionic compound. So let us discuss now what is Born-Haber cycle is all about. Born-Haber cycle now actually talks about the formation of ionic compound. Let us always learn with the simplest compound, sodium chloride. So let us think how sodium chloride forms. Sodium chloride, now if you talk about enthalpy of formation of any compound, how can you write the enthalpy of formation of any compound? One first important factor, you have to choose the kind of elements, and now the elements should be in the standard state of aggregation or in the stable form. So the elements are, one is sodium, another one is chlorine. We know chlorine do not existing as monoatomic, so it has to be Cl2. Remember, it always enthalpy of formation always talks about the formation of 1 mole of an ionic compound that we represent as delta H F. F represent enthalpy of formation. Enthalpy of formation of an ionic compound, now you can represent like this, where elements are sodium and another one is chlorine. So chlorine always diatomic, and remember enthalpy of formation, we have to talk about formation of 1 mole of an ionic compound. So one sodium and one chlorine atom is there. So here two chlorine atom means now half mole of Cl2 is required for the formation of 1 mole of a sodium chloride. So sodium in the solid form, chlorine in the gaseous form, and you are getting sodium chloride in the solid form. So this is the equation for finding the enthalpy of formation of a compound. You can write like this for any compound. This is the way we can write the enthalpy of formation of sodium chloride. Remember, it should be from its element. That's the first point. You cannot now think about formation of enthalpy of formation of any compound from other compound. No. Here we are talking about formation from its element, and this element should be in the stable state of aggregation. So here sodium and chlorine are the two elements. So sodium and chlorine, and sodium it's existing as atomic form, monoatomic form, so sodium plus, but chlorine do not existing as monoatomic form, it's existing as diatomic state. So half Cl2 means why half Cl2, because one chlorine is required, right? So Na plus half Cl2 gives NaCl. This is the enthalpy of formation of a sodium chloride. Like this, now you can write for any compound. Now another way of formation of sodium chloride. So you think, so how another way you can form a sodium chloride? Another way of formation from sodium ion and chloride ion. This is the way now you can think about the formation of sodium chloride, where now sodium ion in the gaseous form, chloride ion in the gaseous form. When these two ions are combined, you will see sodium chloride will be formed. So that's another way you can think about the formation of sodium chloride. So now let us think now how we can reach to this Na plus gas and Cl minus gas, because we know when ionic compounds formed from its constituent gaseous ion, that we will call lattice enthalpy, delta H lattice. So this is now actually talking about the formation of ionic compound from its gaseous ion. So that is lattice enthalpy for you. But to reach to Na plus gas state and chloride minus gas state, from this you have to go through different steps. So let us think how we can reach from Na to Na plus gas. First, now think about sodium in the solid form, so you have to convert sodium into gaseous form. That we will call the sublimation enthalpy, or not. We can simply think enthalpy of atomization. So there we are talking about converting one mole of a substance into its gaseous state. So sodium metal is converted into sodium gas. That we will call sublimation enthalpy. Next, now we converted sodium solid into sodium gas. Next, now here remember we have to provide energy for converting as sodium metal into sodium gas. You have to supply energy. That means delta H sublimation. You can think it should have a positive value because we are providing energy to convert solid into gas. Next, now converting sodium gas into sodium ion. Here now we know the term that's related to this. That we will call ionization enthalpy. Next parameter will be delta H ionization enthalpy for converting sodium gas into sodium ion. So what will be the amount of energy that required to remove an electron from the isolated gaseous atom. So that was ionization enthalpy is all about. Here again now you have to think about the removal of an electron by providing energy. So that means ionization enthalpy will be positive because according to thermodynamics we have to provide energy. So this will be the formation of sodium ion gas. So we got sodium ion gas. Now we have to convert chlorine into gaseous form. How? First of all, now you have to break chlorine-chlorine bond. Remember, chlorine-chlorine is a covalently bonded atom. Two chlorine atom are covalently bonded. So there now you have to break the chlorine-chlorine covalent bond into chlorine atoms. So that now here half mole is there. So let us think formation of chlorine atom in the gaseous form. So how can you convert to this? When you talk about dissociation of a covalent bond, we will say dissociation enthalpy. So we will say half bond delta H half bond dissociation enthalpy. So that parameter will be accounted. Again, you have to provide energy and how much energy that is required to break the one mole of a covalent bond into gaseous atom. That what dissociation enthalpy is all about. Here, half bond dissociation enthalpy because we are talking about breaking of half mole of chlorine atoms, chlorine molecule. So here, the amount of energy that is supplied to break chlorine bond into chlorine atoms. So we converted the chlorine molecule into chlorine gaseous atom. So that thermodynamic parameter we will say dissociation enthalpy. Since half mole is there, this is half dissociation enthalpy. So we converted chlorine to chlorine gas, chlorine gaseous atom. Next parameter we have to convert into Cl minus, right? We have to convert into Cl minus in the gaseous form. For that, another important parameter we will say electron gain enthalpy or we will say electron affinity. So let me represent the thermodynamic term electron gain enthalpy. That's it is the amount of energy that is released when electron is added to an isolated gaseous atom. So this is electron gain enthalpy for you. So when energy is released when electron is added means chlorine become chlorine minus because excess electron will be there. So it will be energy will be released, which means thermodynamically delta H value will be negative because energy is releasing. So we got now sodium ion and chloride ion we got, and when these two are combined you are actually getting a lattice enthalpy. So it will goes like this, right? So next term, after forming a sodium ion in the gaseous form, chloride ion in the gaseous form, now you're going to get the sodium chloride in the solid form. Now, let us think. This is one of the method of formation of sodium chloride from its elements. This is another way of formation of sodium chloride from now by this cycle. So both according to Hess's law, enthalpy change in a chemical reaction is same whether it takes place in a single step or several steps. That's Hess's law for you. Talking about Hess's law. So we are applying a Hess's law to find any one of the missing parameters. Generally, lattice enthalpy are fine. So let us connect Hess's law here. So according to Hess's law, delta H formation of to the compound we talking about sodium chloride will be equal to, because this is the one step process, here several step. It doesn't matter whether a compound formed in a single step or several step, enthalpy change will be same. That's what Hess's law is all about. This is one of the single step formation of sodium chloride. This is several step is there. It doesn't matter, it's not gone through several steps. Enthalpy change is a state function. It depends not only the final value and initial value. So enthalpy change in a chemical reaction will be same whether it takes place in a single step or several steps. So you can combine that Hess's law here. So delta H formation will be equivalent to these all parameters. That is one of the first parameter, delta H sublimation plus delta H ionization enthalpy plus next parameter of dissociation enthalpy, delta H of dissociation, delta H dissociation. Then no, still another factor, that is no, we discuss electron gain enthalpy, delta H electron gain enthalpy plus next factor, delta H lattice. These are thermodynamic parameter, no, in you adding, which is exactly equal to delta H formation as well, because Hess's law suggests that no, it may be the formation of a particular compound maybe takes place through several steps. It doesn't matter if one single step is there, then delta H change in enthalpy will be same, which is equivalent to the change in enthalpy through several steps. So just combine that Hess's law here. Now, so we got an equation, delta H of 0, which is equal to delta H sublimation plus delta H ionization enthalpy plus delta H of dissociation enthalpy plus delta H electron gain enthalpy plus delta H lattice enthalpy. If you sum these all factor, you are actually getting delta H formation of sodium chloride or an ionic compound. So now let us think. Now, if you think about now in terms of thermodynamics, the sign delta H sublimation will be positive because now because you are providing energy. Ionization enthalpy will be positive because you are providing energy. Half dissociation enthalpy will be positive because you are providing energy. Electron gain enthalpy will be negative because here we are talking about now the energy that is released. So according to thermodynamics, this delta H value will be negative. Now think about lattice enthalpy. Here what we are talking about, here not talking about breaking an ionic compound. Here we are talking about formation of an ionic compound from its gaseous ions. So here you have to think, no, energy is actually released. So energy release means no, this again will be negative here. Okay, that you can think. That's the way now the value will be. So sum of all these factors now will give you delta H formation of a particular compound. So this is what now the lattice the Born-Haber cycle is all about. Now let us discuss how you can find the lattice enthalpy. So delta H lattice will be equivalent to, no, here it is here. So delta H formation minus delta H sublimation minus delta H ionization enthalpy minus delta H of dissociation enthalpy minus, let me write no minus because now you can consider that particular sign when you are doing a problem. So I will discuss one problem for you, there you will understand, because now I am putting all positive signs because now summation of all these factors like that. So delta H electron gain enthalpy will give you the lattice enthalpy value. So when we do a problem, you will get a better understanding. Let us discuss. This is the equation. Delta H formation is equal to delta H sublimation plus delta H ionization enthalpy plus delta H sublimation of dissociation enthalpy plus delta H electron gain enthalpy plus delta H lattice enthalpy. So if you want to find lattice enthalpy, how can you find? It is delta H of minus these all factors, delta H sublimation minus delta H ionization enthalpy minus delta H of dissociation enthalpy minus electron gain enthalpy. That will give you the value of delta H lattice enthalpy. So remember the way of finding the lattice enthalpy. Okay, when we're doing a problem, you will get a better understanding. So this is what Born-Haber cycle is all about, especially used to find the lattice enthalpy of a ionic compound. So let us discuss one more point now. What is the real another application? So just discuss point by point what are the applications of Born-Haber cycle and lattice energy calculation. First one, lattice energy calculation using Born-Haber cycle used to estimate the stability of an ionic compound and also stoichiometry of the ionic compound. So what's an idea you're going to get? First, no, the stability of ionic compound. If lattice enthalpy is higher, means no, ionic compound are strongly attracted. So that means no, ionic bond will be stronger. So higher the lattice enthalpy, higher the ionic strength. That's a one point you will get. Another point, stoichiometry. Now from the amount of energy that is released, you can understand the constituent gaseous constituent ions present in the ionic compounds. That's another factor, another important point that you're going to get. So what are the stoichiometry of the ionic compound? Next point, lattice enthalpy determination using Born-Haber cycle is used to account the stability of metal hydrides, polyhalides, peroxides and superoxides. So you can compare the stability of different ionic compounds like metal halides, metal hydrides and peroxides, superoxides, because these all are ionic compounds. So there what's how much stability is, that you can understand from the lattice enthalpy value. Third point, lattice energy data used to determine the evolution of this crystal field stabilization energy. Crystal field stabilization energy is something that we discussed in the coordination compounds, where you will see as we move from left to right in especially in a D block elements. Generally in a D block element, you will see the size of the cation decreases. If the size of the cation decreases, that always helping the stronger lattice enthalpy. So that factor, the lattice enthalpy, definitely going to contribute the crystal field stabilization energy as well, because there we talks about a coordinate bond formation between the metal ions, metal cations and the ligands. So in an octahedral field, the degenerate d orbitals are split into two. One is T2G, especially in octahedral field, T2G and EG. These are the way the degenerate orbitals are splitted. One with a 3 orbital, one with a 2 orbital. So if the electron are occupying in the lower energy level, that always stabilizes the coordination compound. So we require high crystal field stabilization energy for a stable coordinate compound. So lattice enthalpy going to be a definitely important factor in determining the crystal field stabilization. The calculation part is we will discuss in another section, where definitely if you going to determine a crystal field stabilization energy in a coordinate compound, lattice enthalpy going to be an important factor. You can think like that. Next point, comparing the solubility of ionic compound. Yes, I know we already discussed. If you want to dissolve an ionic compound in water, or in any other solvent, lattice enthalpy going to be an important factor. Higher the lattice enthalpy, lesser the dissolution of an ionic compound in a solvent. Last point, lattice enthalpy used to determine the electron affinity as well. So you can find any factor. Now, if you provide other delta, other lattice enthalpy parameter, enthalpy parameter, you can find the other factor like delta S formation. You can find sublimation. You can find ionization enthalpy. You can find dissociation enthalpy. You can find electron gain enthalpy. You can find lattice enthalpy. You can find if you provide other factors. So using this equation, you can find the thermodynamic parameters like this. So that's another application you can think related to Born-Haber cycle and lattice energy determination. So next class we can discuss the problem related to Born-Haber cycle. So please go through this section and understand it very well, so that now we can easily do the problems. Okay, thanks for listening. Let us wind up. Thank you.